Hello everyone, thank you for watching this video. Today, we will present our work titled KTPFormer, Kinematics and Trajectory Prior Knowledge Enhanced Transformer for 3D Human Pose Estimation. This work has been accepted by the Computer Vision and Pattern Recognition Conference 2024. First, let's briefly introduce 3D human pose estimation. 3D human pose estimation aims to predict the 3D coordinates of human body joints from the input of either monocular 2D images or video sequences. Recently, the 2D to 3D pose lifting methods which infer the 3D poses from the intermediately estimated 2D poses have achieved state-of-the-art performance and are widely prevalent because of the remarkable performance of 2D pose detectors. Our method follows the strategy of 2D to 3D lifting. Next, let's introduce the motivation behind this paper. Existing transformer-based methods for 3D pose estimation model either the spatial correlation between joints within each frame and the pose-to-pose or joint-to-joint temporal correlation across frames. These transformer-based methods all use linear mapping where 2D pose sequences are tokenized into high-dimensional features and disrupt the inherent anatomical structure and temporal sequentiality of the pose sequence. This may lead to the problem of attention collapse, a phenomenon denoting a circumstance wherein the self-attention becomes too focused on a limited subset of input tokens while disregarding other segments of the sequence. In order to solve the above problems, we introduced two novel prior attention mechanisms in the transformer, namely kinematics prior attention, KPA, and trajectory prior attention, TPA. KPA first constructs a spatial local topology based on the anatomy of the human body. The way these joints are physically connected to each other is fixed and is represented by solid lines. Then, KPA uses a fully connected spatial topology to calculate the joint-to-joint attention weights, called simulated spatial global topology. Next, KPA combines the spatial local topology and the simulated spatial global topology to form a kinematics topology, where each joint has a learnable kinematic relationship with each other. Similarly, TPA connects the same joint across consecutive frames to build the temporal local topology, and it constructs a simulated temporal global topology by exploiting learnable vectors, dotted line, to connect the joints among all neighboring and non-neighboring frames. Then, TPA combines the two topologies to obtain a new topology called joint motion trajectory topology, which allows the network to learn both the temporal sequentiality and periodicity for the joint motion. The KPA and TPA modules are combined with vanilla multi-head self-attention mechanisms and MLP to form the kinematics and trajectory prior knowledge enhanced transformer, KTPFormer, for 3D pose estimation. Besides, KPA and TPA are designed as lightweight plug-and-play modules, which can be integrated into various transformer-based methods, including diffusion-based, for 3D pose estimation. For example, we introduce a diffusion process to our KTPFormer and use it as the denoiser. We gradually diffuse the ground truth 3D poses to a random distribution, and learns a denoiser conditioned on 2D keypoints to recover the uncontaminated 3D poses. As shown in Table 1, the diffusion-based KTPFormer achieves the state-of-the-art result 33.0 mm in MPJPE and 26.2 mm in PMPJPE on the human 3.6M dataset using the 2D poses detected by CPN as inputs. Table 2 shows that the diffusion-based KTPFormer achieves the SOTA result 18.1 mm using ground truth 2D poses as inputs. As shown in Tables 3 and 4, our KTPFormer also achieves SOTA results on the MPI, INF, 3DHP and HumanEVA datasets, respectively. As shown in Table 7, our method brings about noticeable improvements in all the transformer-based models in terms of MPJPE, with very slight increases in the number of parameters and flops. As shown in the figure, KPA can make the spatial self-attention mechanism more reasonably allocate attention weights between the joints. TPA can also enhance the sequentiality and periodicity of temporal self-attention. Our method demonstrated robust result of 3D pose estimation on the video containing highly dynamic human motions. Thank you for watching this video.